We're continuing with review for pre-calculus, laws of exponent and logarithm. Laws of exponents. Let a and b be positive numbers and x and y be real numbers. Then base b to power x times base b to power y is equal to base b to power x plus y. B to power x over b to power y is going to be b to power x minus y. B to power x to another power y is equal to b to power x times y. If the two base multiply together to power x, then you will have a to power x and b to power x. So b to power x is equal to a to power x times b to power x. A over b to power x is going to be the quotient. A over b to power x is going to be a to power x over b to power x. Laws of logarithms. If m and n are positive numbers and b is bigger than 0 and b is not equal to 1, then logarithm base b of m times n is equal to logarithm base b of m plus logarithm base b of n. I usually call this log of product is equal to sum of logs. Then log base b of the quotient m over n is equal to log base b of m minus log base b of n. Log base b of m to power n is equal to m power comes down n log base b of m. Log base b of 1 is equal to 0. Log base b of b is equal to 1. Now let's do a few examples. Examples for law of exponents and logarithms. First, log base 3 of 1 over 27. Let's remember 1 over 27, and that requires a quotient law. So it's log base 3 of 1 minus log base 3 of 27. Then 27 is 3 to power 3. So we can use any base of 1 is going to be 0. So we end up with 0 minus log base 3 of 3 to power 3. Now, inside the log, we have an exponent. So exponent comes down and it becomes negative log base 3 of 3. But we know what log base 3 of 3 is. That's 1. So the entire thing is 1. What about log base 5 of 125? On this one, rewrite 125 into 5 to power 3. And it's log base 5 of 5 to power 3, which is 3 times log base 5 of 5 equal to 3. Now let's do a few logarithm laws of logarithms. Natural log of x plus natural log of x minus 1 equal to 1. And this is an equation. How do we solve this? We use the law of product, natural log of product equal to sum of natural logs to combine. So the first thing that we do is we use the opposite direction that was given in the previous page. And so natural log of x plus natural log of x minus 1 is going to be a natural log of x times x minus 1 equal to 1. Now, use the inverse property of natural log and and we end up with e to the power natural log of x times x minus 1 is equal to e to the power 1. At this point, we don't actually have a natural log anymore, and this becomes a polynomial equation. the polynomial is of degree 2 because it's x times x minus 1. Degree 2 polynomial means a quadratic equation. So rewrite it as a quadratic equation, and it's x squared minus x minus e equal to 0. Use your quadratic solution to find two solutions. One is 1 minus square root of 1 plus 4e divided by 2. The other one is 1 plus square root of 1 plus 4e divided by 2. Make sure that there is no extraneous solution. The first one actually is a negative value and cannot be plugged into the original. Therefore, the first one is not part of the domain, and the second one is the only solution. Let's move on to part 2 of the logarithmic and exponential equations. When you have an exponential like that, what you want to do is you want to undo the exponential by taking the logarithm. If no other step is needed to be taken, that's the first step. So you start with e to the power 7 minus 4x equal to 6. Take the natural log of both sides so you can get the exponent by itself, and then the other side it will be natural log of 6, which is just the number. So you technically got cleaned up any logarithm or any logarithm expression or exponential expression out of it, because ln of 6 is just a number now. It's not ln of an expression with x or with an input variable. Now at this point, look at the variable. Variable is x, everything else is numbers, and x is just to power 1. This is a linear equation with respect to x, and so solve it. And by taking maybe subtracting 7, or maybe subtracting natural log of 6, and then adding 4x and dividing by the 4. And so what happens every time with logarithmic and exponential functions is that you get rid of those expressions and turn them into a polynomial function if you can, and then you solve. Another example that actually we use a lot of laws of exponent for is to factor an expression like this. 18x plus 2 to power negative 2 times x minus 1 to power 1/2 minus 6 times x plus 2 to power negative 1 in x minus 1 to power 3/2. So in these cases, what you want to do is to find basically each common factor with the lowest exponent. Over here I have 16, and I have 16 and I have 6. 16 is 3 times 6, and so there's a common factor 6 between the two. Basically, see, this is the first term, this is the second term, and 6 is the common factor. Then I look at another common factor between the two terms, and that would be x minus 2. And x minus 2, one is to power negative 1, the other one is to power negative 2. So this is the lowest exponent. That's the factor to the lowest exponent. The next one to see is x minus 1, and x minus 1 to power 1/2 or 3/2. This one again is the lowest exponent. And so I end up with 6 times x plus 2 to power negative 2, x minus 1 to power 1/2, as the factor. Okay, and so when I'm factoring 6 out of 18, we end up with what is, so each term out of the first term, if I factor out 6, 3 remains, and then if I factor x plus 2 to power negative 1/2 to the power negative 2, 1 remains, x minus 1 to power 1/2, 1 remains. So 3 is what is remaining out of that one after the common factor. Over here, after I factor 6, nothing is remaining. After I factor x plus 2 to power negative 2, let's say factoring means dividing, right? So what is remaining is going to be, according to exponent law, is going to be x plus 2 to power 1. And so that's that. Then x minus 1 to power 3/2. If I factor x minus 1 to power 1/2, again I'm dividing, another exponent law. Basically, it's always the other way around also. If you look at the exponent law of 2 pages ago, and you see that you can put x minus 1 and then power of top minus the power of bottom, and that would be basically 1. Over here was negative 1 minus 2, which is 1 also. So both of them came out to be 1. Now that the factoring is done, the next step is to basically clean up as much as you can. And so the cleaning up over here is 3 minus square root of 3 minus x plus 2 times x minus 1, excuse me. And so that when you FOIL x plus 2 times x minus 1 and subtract that from 3, you end up with negative x squared minus x plus 5. And then the last step, this is something that we do a lot in chapter 4. Basically, this type of factoring and simplification is needed, so we can find the domains and 0 of the function and so on and so forth. And so in here, the last step that you want to take is that convert x plus 2 to power negative 2 into the denominator, basically. Over here, they were in the denominator, but we wrote them as a negative power. Now here, we bring it back to the denominator to a positive power, and then write down power 1/2 as a square root, and that makes it easier to compute. Now let's simplify an expression like x to power negative 2 times y, square root of z to power 5, and then x times square root of y to power 4 and z. And so when you simplify this one, remember it's z to power 5/2, and so that's the first thing to remember. Then in the bottom, you can separate if you have two different bases, that's y to power 4 times z, and then to power 1/2 overall, then you get y to power 4 to power 1/2 and z to power 1/2. And so that's the first step that you want to take. At this point, you want to use the other exponent laws to simplify. How do we do that? If you have multiple terms with x and m, you want to simplify that. And over here, I have x to power negative 2 on the top. Realize that that should be in the denominator, so x to power 2 came in the denominator instead. And so multiply by x, and then y to power 4/2, which is going to be y to power 2. Over here, when you're taking the square roots, you have to be careful if it's needed to put an absolute value in it or not. And in this case, you don't have to put absolute value because it's y to power 2. And z has to be a positive value because it's in the domain, and therefore that one also you don't have to have the absolute value around it. So the next part is to simplify 5/2 and 1/2. So z to power 5/2 over z to power 1/2. It's the quotient with the same base, and so you subtract the exponents and you get z to the power 2, x to the power 2 times x to the power 3, and y to the power 4/2 is just y to the power 2 basically. And then simplify it with a y on the top, and you get y in the basically in the bottom. And so the entire thing simplifies to that. So one of the interesting properties of Exponent, many real life events can be modeled by exponential functions. And one nice property of exponential function is that function with exponential, many of them have horizontal asymptote. And so the discussion of horizontal asymptote when exponential comes in is always a necessity to understand the model of mathematics that you're using. And so let's do an example for that. Graph the following function indicating its asymptotes. And the function is y equal to negative x to the power negative x plus 1 plus 1. Here, what you see is this part is the exponential, and it's sort of given that when the exponent goes toward negative infinity, this part is going to go to 0, and therefore you basically, as x goes to positive infinity, making the exponent going to negative infinity, you will end up with y equal to 1 as your horizontal asymptote. The other way of thinking about it is this is an exponential function that was shifted up by 1. So the horizontal asymptote has to be shifted by 1. So that's one thing to remember. Then you want to plug in a couple of points. For example, x equal to 0 to get the y-intercept, and maybe setting y equal to 0 and solving for x to find the x-intercept, and that gives you the approximate shape of the function. By the way, when you set the y equal to 0, then you're solving an exponential equation, and basically the same routine that we did in the previous slide.